This talk is supposed to be what has Dave been doing for the last 10 years in 90 minutes. So we made this whole plan, and it may come off, and we might need to end early and do more talking later. So I don't know how this is going to fit. All right, we will see. Anyway, for the last 10 years, you probably know that I spent a bunch of time working on the design of the Swift language and its standard library. But for me, that wasn't about Swift, but about digging into these two powerful ideas. Oh, and I forgot to mention, Dimitri here is supposed to do the last third of the talk, if timing all works out, as it should. So, one of the many things I learned from Alex Stepanov is that in the work of programming and library and language design, there's a process of discovery. There's an underlying truth about the nature of programming, and that actually exists. In fact, as Sean Parent likes to remind me, it's a physical reality that's dictated by the way hardware is designed and built, which in turn is on the laws of physics, right? Another thing I learned is generic programming is a really beautiful idea that should get more uptake. But I fear that the meaning of generic programming has been lost. So what do we mean by generic programming? Alex? Okay.
I think that what we were advocating is programming with templates, or especially a term some of your younger generation might have heard, template metaprogramming. Perish the thought. We had nothing to do with template metaprogramming. At least I did. Well, neither did Dave.
Neither did Dave. Now, unfortunately, he's not talking about me. Yeah, he's talking about his collaborator, Dave Musser, who's the author of the great intro sort algorithm. In fact, I wouldn't be surprised if this whole rant wasn't inspired by the fact that I co-wrote this book about template metaprogramming, which incidentally, Alex wanted nothing to do with, okay? Metaprogramming, just to clarify the domains, is about writing programs that manipulate programs, like compilers, which is really cool. And template metaprogramming is about using stupid template tricks to do it. So, don't read my book to understand generic programming. These two are excellent references, both co-written by Alex. Okay, back to you, Alex.
We were trying to understand algorithms and data structures in the most abstract setting. The reason we use templates because it was a convenient technology. Again, we do not view template metaprogramming as anything related to our research. Maybe it's an interesting area, but even that it's somebody else's opinion, not mine.
Okay, so I think you get the picture. Now that we've got that completely blotted out, the focus is on generalizing algorithms so that they can be used with many data types, including ones you don't know about. And really, this is algorithms as the primary abstraction that you're dealing with. And I'm going to go off script for a second. I think algorithms are underrated as an abstraction. That's where the compute is. That's what computers do when they're not being, no damn good, right? That's what computers do. So generic programming really honors that. One of the things that Alex is leaving implicit here is that we want to do it without loss of efficiency compared to the non-general version, okay? And another thing is when he says understand, we're not satisfied with some kind of wishy-washy half understanding. We need to be able to describe what these things do at a formal level, right? And that implies a clear specification, which becomes important in this talk later, right? So here's a good example of generic programming. This is one of my favorite papers. It's a very old paper by Matt Ostern, but still one of my favorites. And here he's exploring how to generalize algorithms to take advantage of the segmentation inherent in common data structures like a deck, for example, or a circular buffer, or a hash table, or a B tree, which you can see has multiple levels of segmentation, right? Or a matrix divided into parts that each fit into various caches and the machine's register set, right? If you care about performance, that's important, even if it's not in the data, in the memory layout, okay? So it turns out that if you linearize DEC the way a standard iterator does, you pay about a 20% performance penalty to do a complete traversal. So what you want is a loop at each level of hierarchy in the data structure, right? A loop across these, and a loop across these, and a loop across those. And they should be nested, and that's what should fall out of the generic algorithm. So Matt came up with a beautiful concept, segmented iterators, that allow hierarchical algorithms to be progressively built on the non-hierarchical ones. And since we're at Boostcon, I should also mention this library as a great example. In addition to graph concepts, they also discovered a very unusual hierarchy for building algorithms using visitors. Okay, note that Alex had no problem at all being associated with this book. All right. So that's generic programming. What about value semantics? So Jeff, so what about value semantics? We have some intuitive idea of value semantics, but actually understanding what it means has been an open question for 13 years at least. So I'm just going to read this out loud. This is a blog post by Greg Colvin from the very first Boostcon, his report. He said, I head over to the session on value-based programming to be co-taught by Kevlin Henney and Jeff Garland, except that Kevlin is still unconscious in Denver, recovering from the delays of his 2 flights from London and waiting for the noon shuttle to Aspen. So Jeff has to defend Kevlin's slides from the withering criticism of Dave Abrahams, Howard Hinnett, and others. I told you there were going to be things I'd have to apologize for.
Fair enough.
Okay. The basic idea seemed to be that if one crafts one types to be just like an int and does everything by value and not by reference, then good things ensue. The contention was around whether Kevlin had defined value type clearly enough. And like, for instance, is a pointer a value type? What about a smart pointer? So I do need to apologize to Jeff and Kevlin, not just because I criticized them witheringly, but also because it took me until about 2020 to actually answer this question that I was pressing them on. And I've been in the process of like refining that answer since. So, but maybe we can agree at a fundamental, as a basis, that int is a prototypical example of a value type. I'm hoping we can start there. Any objections? All right. So maybe the easiest answer to the question, what is value semantics, is that it's not reference semantics. That's the first thing a lot of people say. And it can be useful to look at an example of that. So let's say you've got a program with components X and Y, and it's handing out bunnies. And so it gives a bunny to X, and it gives a bunny to Y, and then X gets to thinking it would rather have a more robust animal like a camel. And so X gets a gene sequencer and turns its bunny into a camel. Much later, Y goes to check out its bunny and finds a camel. Okay, we call this spooky action at a distance, with apologies to Einstein. And of course, what's happening here is the program is actually handing out references to the same bunny, right? Okay, people who program with references all the time have come up with a technique called defensive copying to ensure that they don't inadvertently share mutable state. And that's a big deal in Java, for example. And when references proliferate, you more often end up with something like this, where a local action has a whole set of non-local consequences. And as Sean, again, is fond of pointing out, you end up with some algorithm encoded in all of those interactions. And, that you can't reason about, and because it's incidental rather than explicit. It might even go into an infinite loop. But that's not the extent of it. Right? Another problem comes up around mutation, because during a mutation, you typically have to break invariants and then restore them before they become observed, right? But if you call out to some other object while the invariants are broken, you might find that the chain comes back, right? And to inspect the object that's under mutation. This is what reentrancy means. It's not about control flow. The name suggests it's about control flow, but I only realized in the last 2 years, reentrancy is about access to mutable state, right? And the classic reason a function isn't reentrant is that it's using a mutable global, okay? And race conditions are just another version of observing broken invariants. So I'm not going to belabor that. We all know that reference semantics and race conditions are good friends. Okay, another scenario actually leads to spooky local action, right? You could be doing a non-mutating operation and inadvertently cause the current object to be mutated, right? And suddenly you're back in the original object with a whole new state. It's just pretty spooky and really hard to debug. So it might not surprise you to learn that immutability is becoming like all of the rage in JavaScript. It's like everybody wants to work with an immutable library. There's all this mutability in the language, and nobody wants to touch it, right? And that's a pretty extreme response, but when all you have is JavaScript, that's all you can do, really. Okay, so back to what we mean by value semantics. That's what it's not. I'm going to say we mean two things. So the first thing is what I'm calling regularity, after Alex's regular concept, and that's about the laws about copy, assignment, move, and their relationships, right? That X is always equal to X, and copying a thing makes a thing that's equal to the original, okay? And the other one is independence, right? Independence is about the visibility of mutation. It's the idea that when you have a variable of value type, your other code can't do anything to affect your locally available variable value. And nothing you do to the value can be observed by other code. Lastly, it's as thread safe as int. What do I mean by that? Most people don't think of int as a thread safe type. Well, it isn't in most ways, but you could do worse, right? A shared pointer with non-synchronized reference count, that's going to race even if you pass separate copies to different threads, right? So a value type should be, as a baseline, as thread safe as int. You should be able to manipulate distinct instances in distinct threads without racing. Okay, that's what that says. Oh yeah, so some sharp person in the audience is probably, wondering how this all fits into it. You're all detail-oriented C++ hotshots, right? So you probably already thought of this. We have a prototypical value type instance X, right? Because it's an int, and then we form a reference to it and modify X through the reference. Oh, yeah, that's a Swift instinct. So we'll come back to that. Thanks for noticing. Can I make it on the fly correction? Nope. I'm going back to the slides. Okay. Right. So we have this wrong example that that's still a problem. So obviously, none of you were thinking this because you all know better than to put the ampersand there. Sorry. Anyway, right. So we need some way to cordon off this usage. So for now, let's just make pointers and references an exception, okay? Now, I've got to acknowledge this is a hole big enough to sail the Vasa through, right? I mean, you can barely, excuse me?
If it could sail.
Yeah. It's in a museum now, but you know, if you can barely do any mutation in C++ without involving a this pointer, right? And references are everywhere. We'll come back to that, so please, you know, just bear with me. So, things to notice about these two categories. First, regularity is really easy to specify, test for, and satisfy. Notice that the laws are all full of code, right? It's hugely important, but it's simple. It's about what must be so when you do these things, right? When you compare these things, this must be true. When you copy these things, okay. Independence is sort of the opposite. It's about what must not be so. And that's a universe too big to test, and it's a lot harder to get a grip on. But there's another fundamental reason that that independence is difficult, which is that it rests on these things that we don't have a formal definition for. Like, what does it mean to write, read, or affect a variable, right? The answers to these questions all fall out of one more fundamental concept, which is, what is the value of X? So we're kind of back where we started, Jeff. Okay, well, if you look in the standard actually has a pretty good foundation for starting to think about this. So this is 861. So first, it defines the object representation of an instance T as its bytes in memory, right? The raw stuff, Lisa. Stuff you like, right? And then it defines the value representation as the set of bits that actually participate in representing a value of type T. So that suggests that the value is a thing. The standard doesn't go on to define it much more than that, but there is one important thing you see here. They're really only talking about trivially copyable types here, but that's only because the set of bits in the object representation. I think this applies generally. So what they say is a value is one discrete element of an implementation-defined set of values. And when they say implementation-defined, they usually mean they're talking about your compiler. But here they couldn't possibly be talking about your compiler because users can define their own trivially copyable types, right? They're talking about the implementer of the type, right? So that is exactly the question. What do you mean value? Yeah, the type author needs to make that choice, needs to make a decision, right? And that choice both reflects if they've worked out the meaning of their type and determines the meaning of the type. You choose badly, you've got a bad meaning type. All right. So that is the operative question. So let's look at an example. The heavy purple box you see here surrounds the object representation of a widget. Let's call that a widget, okay? So the object representation is the bytes in memory. But what is the value representation? Well, that depends on how the widget's author understands its meaning. In this case, I'm the author, okay? So I'm going to give you the answers, but the answers might be different for another type that could be described by the same diagram. All right. So first we have namelen, right? That determines the number of significant elements in the name array. And so since the name is notionally part of the value, namelen is clearly a part. Okay? So that's a part of the value. Now, next there's the name itself, right? Now, I consider two widgets with different pointers to name data, but equal contents in their name data to be equal, okay? So name itself is not part of the value. So we can color it gray. Next, there's the data pointed to by name, right? So that's, you've got exactly name-len elements that are part of the value. Finally, you've got this pointer to a shared cache, right? Now, widget uses the cache to respond to queries faster, but the cache doesn't otherwise affect the widget's behavior. So neither the cache nor its pointer are part of the value. It doesn't really matter what's in the cache, the widget will give you the same results. All right. So let's look at one more case. Suppose you had a sibling pointer in here. So what is this describing? This describes a relationship between the widget and some distinct entity that's not part of the widget. I'm telling you that. I'm telling you the sibling is not a part. And you can ask yourself, so what about the bits of that pointer? That's why it's half colored, right? As the type author, you have to decide whether that relationship is part of the value of a widget. You can ask yourself, should two widgets with different siblings that are otherwise equal be considered equal? That's a way to answer that, right? And I'm going to answer, yeah, those should be equal. So sibling is really just a convenient place to store this relationship and not part of the value. All right, that's because I get to design this type. Okay, so the upshot here is that the yellow parts show you the whole part relationships, right? And it's these parts that need to be copied when you make a copy, compared for equality, etc. Incidentally, C++ allocators are part of the reason they're so problematic is that they invert the whole part relationship, right? Can't store the thing you're a part of in you. That breaks the value model, okay? So I want you, also I want you to get the whole idea of deep copy out of your vocabulary. If you're using that phrase, it shows that you don't understand the boundaries of your value, right? There's only a copy. You copy the parts. You don't copy the other things that are related in other ways. Same goes for shallow copy, right? And, no deep equality, no deep hashing. They're all in the same bucket. Okay. Next, when you aggregate value types into these whole part relationships, which is the usual case, usually you don't have a lot of these and those, right? All these operations can be composed out of the parts by a compiler. So regularity and independence get tied together right here. And there's one last consequence, because we said that distinct instances could be freely used in distinct threads. Any shared state, like the cache here, needs synchronization, right? Or the APIs that use it become unsafe. There's nothing wrong with an unsafe API as long as you know it. But yeah, if you want a safe value type, then that's required. Okay, Dimitri here and some of my former colleagues at Google Brain and I wrote a paper to explain these ideas. And we were motivated to do that because of 3 shocking facts. At least I found them shocking. So first, a lot of people actually have a hard time imagining the existence of independent mutable instances. Like, we were talking to a lot of Python programmers at Google Brain, for example. That's what all the AI gets done in Python these days. And it set the model for these people. You know, it's a mutually reinforcing thing. Many languages, like Python and JavaScript, can't express independent mutable instances. Right? There's no way to keep a reference in JavaScript from getting copied. Lastly, and this really blew my mind, is that the formal languages used to describe the semantics of mutating programs in computer science, they all have reference semantics at the foundation. Now, Dimitri explained to me just in the last 12 hours that there's a good reason for that. But still, I mean, it really is a good reason. But still, it colors the way computer science researchers are thinking about computing, right? Okay, so our paper, it totally ignores regularity, and I'm going to pretty much ignore it for the rest of this talk. But if you're wondering why we say mutable value semantics, it's that in pure systems, immutable types are trivially independent, right? Okay, all types in a pure system. So does anybody know when we started this? Because now I realize I don't know how long I've been going. 30, okay, thank you. Okay, so let's do a quick exploration of C++'s mutation model using a simple example. I've got a sort function here that takes a comparison predicate. Now, even without seeing the body, I can tell you it's wrong. Does anybody see what's wrong with it? Yeah. Well, how are you going to sort the thing otherwise if you can't mutate it? Okay, well, that's not what I have in mind, but yeah.
Predicate accepts the ints by value.
Why is that wrong?
Well, given the comment that it's looking at the values of the elements, implying that the indexes are different, and you can't get the indexes from the values.
No, this doesn't have anything to do with indexes. Okay, I'm going to tell you, okay? Its specification makes a promise it can't keep. Okay, a function that doesn't fulfill its specification is broken. I hope we can all agree on that, right? And so, quick, how do you write lots of code without ever writing a broken function? Exactly. All right, this is a good lesson to learn. Okay. Don't ever document anything, and you will never write an incorrect function, right? All right. I will show you the unkeepable promise by writing a horrible, no good, very bad comparison predicate. Okay? That's right. It modifies V before doing the comparison. See that? Okay. That's very bad. So what happens if I use that function to sort V? Well, it depends on what's in the body of sort, right? What actual like details of how sort is written. But if I use just sort of the obvious implementation, it's undefined behavior. If you're lucky, it crashes because the iterators are just pointers and the vector's memory gets reallocated out from under them, right? But I've also seen 1, 2, 3, 1, 1 come out of this. Okay. So we really need to say this function only works if compare doesn't modify S, right? So once we've done that, now we can find the person that wrote the horrible, no good, very bad, awful comparison operator and blame them for violating the terms of the contract retroactively, so they clean up the mess and we're off the hook. Right? We just saw an example.
It's horrible.
Yeah. Yeah, S is V, right? S gets bound to V here. V is a global. V is getting modified in the comparison function. But this is just a very blatant way of producing reference semantics, right? Because I have a global. This kind of interaction can easily happen, right? Without globals, right? If there's shared state under the covers. All right. But what is this requirement? This says that S and compare need to be independent, right? It's exactly that property of value semantics. And it's not specific to this algorithm, in fact. And when I realized that, it hit me like a ton of bricks. When I realized this, without independence, the effects of a mutating algorithm cannot be specified. Think about this for a second. You're mutating your parameters, but you're also mutating some state that's part of something else that you don't even have a way to describe. Because if you're documenting the function, all you can describe are your parameters, right? There's an effect over there, and you can't describe it, right? And since an algorithm, it gets worse, since an algorithm is just any function, this doesn't just apply to things that we think of as algorithms, right? Every single mutating operation from a single machine instruction to a database transaction really depends on independence for its correctness. It might be an unstated requirement, but is there. In fact, this is very real for the C++ standard library. I still remember long after standardization, we started to discover there were loads of places where we simply hadn't considered what was supposed to happen when we pass multiple overlapping things by reference, right? And here you've got essentially the vectors getting passed by reference to its, by pointer to its member function, right? And there's a reference to its front that's also getting passed in. Okay. Yeah, so then the standard acquired a whole bunch of arcane language to shore up, these cases, right? Which nobody ever intended to they weren't really thinking about supporting those. Yeah?
Is that now supported or is it explicitly forbidden?
No, that I believe is supported. I believe, but you shouldn't ask me because I haven't been around a committee meeting in 10 years, so.
No, implementations are required to make that work.
Yeah. Okay. So in fact, sorry? Okay, that's a good point in favor of what I'm saying here. It's sad that we had to accept an inefficiency in order to make that work. Okay. But I'm going to claim something even more strongly. I'm going to claim that your mental model for references is the same as the people who originally specified the STL as Alex's, right? I'm going to claim that independence is in your mental model for references, right? Nobody documents this, right? Okay, Lisa can be the exception to this one. That's fine, that's fine. When I say nobody, yeah, I'm going to have a few nevers and nobodies. The quotes are around them. Lisa's an exception to the nobodies, okay? So, I don't normally consider what happens when my reference parameters overlap, right? Given that independence is so important, do you think maybe we can do a little bit better than bad programmer? Maybe we could use the language to help us avoid having to write this kind of requirement and just make it impossible for our colleagues to mess up. Well, actually, in C++, there's a little known language feature called pass by value and return. And people don't use pass by value very much anymore. But it can help us. So let's turn this into pass by value. Okay, so now we're getting the thing passed in. we have to get the result out somehow. So we've got to copy that input type into the return, right? The thing that we were mutating. We fix the documentation. And now we can drop this requirement because sort knows that nobody can touch this S, right? It's got the only one. And, oh yeah, we have to reassign V here. So this form is what's known as a functional update. And there's a general transformation you can use on any mutating function, right? You take all of your by reference parameters, and B, right? And you turn them into by value parameters, and then you bundle up their updated values into a tuple with the result. And at the call site, you update your all the former by reference parameters via assignment after the call. Okay. Yes.
This could still be a problem if somebody passes in like a move vector or something like that.
A what? A what vector? A what now? Is this a thing I've not heard of? Is there something called move vector?
No, just a move of some vector going into the argument for S.
Oh, yeah. So, okay, sorry. The question was, this could still be a problem if someone passed in a moved vector. Yes. I mean, what you're pointing at is one of the many gaps that you can get in, where you can get in and disrupt any kind of like safety or certainty in C++, right? Right? Because what we have is we have these non-destructive moves, which are logically destroying the value, right? But you can still go and look, right? So,
but if you still would have the update in less, then it would be, the error would be on the user side because the user moves from the object.
This is brilliant. We can blame the user after this transformation. I love it. I love it. All right, so you got me off the hook. Thank you. Well, yes.
Well, you're not quite off the hook.
Well, I'm off that hook. No.
The standard
Okay.
guarantees that the data in the vector is stable through moves of the vector.
Mm-hmm.
So you can keep the data pointer and then move from the vector and still use it. And standard says that's fine.
Oh yeah, sure. Yeah, I mean, so I think what you're saying is you went through the Vasa hole is the problem, and I told you couldn't go through the Vasa hole. All right. So you don't get to appeal to pointers and references here. All right. I'm asking you to take a constrained view of C++. And if you don't take a constrained view of C++, there's almost no way to get a grip on it. Like, for example, the constrained view that your by reference parameters actually have independence, for example. All right. Yeah, and Lisa, I know that's cheating. I understand. So, okay. So, of course, because this is C++ and we need to explain everything to the compiler, there's one more thing we have to do to make it efficient, and that's pass this by move, right? Okay. But nobody does all this, right? Nobody does this. Even though it technically would make your code more robust, it's not horribly inefficient, really. You're paying for a move that you didn't, or two moves. I guess just one move that you didn't in the original case. It depends on the surrounding code. Anyway, nobody does this. Yeah.
If somebody does this, what happens if sort encounters an exception somewhere in the middle? Then just V is unusable.
Mm-hmm. Well, V is still destructible. I mean, that's what happens whenever you're mutating a thing and an exception happens, unless you happen to have the strong guarantee, and that basic guarantee is perfectly workable. And go to Sean's talk later to hear about it. He's going to take apart all my theories on exception safety. Apparently, he's been needling me about how I'm going to hate his talk. So we'll have to see. Yeah.
Why not pass S by R value reference to make the move obligatory?
Passing S by R value reference doesn't make a move obligatory. No, nobody has to move out of it. It's just a reference. You can just leave it alone.
It makes it obligatory to write move or
Otherwise it's all form.
Oh, okay. I'm not.
new value.
Yeah. Sure. Sure. If you want to do that, okay. But now you're dealing in references again. You have less certainty, right? Okay. My point is, here we're using this sort of the built-in things in the language that give you some guarantees. Pass by value gives you some guarantees, assuming you write your types sanely, right? And they're value types and not, anyway. Okay, but nobody does this, which led Chris to say this to me one day at Google. And I thought, wow, that's true. C++ has all of this support for value semantics, but we're constantly subverting it with references and pointers. And what he meant was that because C++ eagerly copies the element data of containers, nobody really wants to pass them by value, right? And actually, Rust has this property too. And Swift also has this property, although it's mitigated by copy on write, which we'll see more about later, okay? But all of this rewriting that I was showing you is cumbersome and it's a bit verbose. Maybe that's why nobody does it, right? So what if we had a language feature that would give us those semantics with the move and everything else, but avoid the reassignment and the rewriting? Just let the compiler do the transformation internally. I would call this feature in-out. Okay, so let's use my feature here, replace that reference with my new keyword in-out. Right, the compiler would rewrite my function declaration of sort to use pass by value and then return the updated result and would rewrite my call to sort as a functional update down there, right? Incidentally, I already donated a kidney to ISO for no accept. So a horrible language feature for which I apologize, many apologies. Incidentally, so I need a volunteer donor for this one. Anybody, do I have any takers?
I think Herb Sutter is on it.
Oh. Yeah, but unfortunately, Herb doesn't want to make this mean the right thing. He just wants this to be a regular mutable reference.
His kidney.
That's true. His kidney, his feature. Good point. Okay. Anyway, this is basically the mutation model that Swift uses, except that Swift doesn't actually need to move to pass something in out. There's just a mutable reference under the covers, but with all the same guarantees that we get here. So here's the same function in Swift. Should look pretty similar. I'm going to show you some Swift code. I'm not going to explain everything about Swift syntax. I think it's mostly going to be kind of obvious, but do feel free to stop me if something really is catching you up.
How often does that really help? Because if I have a comparator that actually changes the vector, there's probably some programmer intent of doing so. And that programmer intent is probably bad.
How often does this really help? So I'm repeating the question. I'm repeating the question. Yes, you're right. I'm repeating the question. So the question is, how often does that really help? Because there's usually some programmer intent behind this, and the programmer is doing something wrong and bad, right? And so code will break in other ways. And yes, it does. And when it breaks in other ways at compile time, that's a very good thing. But it doesn't always. In these global cases, I will show you, you can't always do it. Okay. 15 minutes remaining. Is that what that says? Okay, we're going to do a part of my talk, and then And then, you know, maybe next year I'll come back and do the rest, or we can talk at break. All right. Sorry, Dimitri. All right. Notice there's one difference that it's worth pointing out, this ampersand. So that's what I was referring to earlier. It's not an address of operator. It's a sigil that announces to the reader that V is being mutated. Okay, that really clears up what's going on at the call site, just to have a little marker. So, to your question, what happens here if I try to use that terrible, awful comparison function? I'll just append V sub 0 to V here. Okay, so now we can see it. Notice also that when we mutate via a method like append, there's no ampersand. And the method name is expected to reflect that it's mutating. That's just the way it's done in Swift. Okay, so if I run this in Xcode, the program crashes. Great, well, I hope you'll bear with me for a minute while I explain why my wonderful feature is crashing the program. First, this is a safety check inserted by the compiler. Okay, it's not undefined behavior, at least, which is what you would get if you use the C++ functional update with the move in it for complicated reasons, because move and C++. But if you take out the move and let it copy the vector, to your point, what ends up happening is the pushbacks are silently discarded. Okay, which that's a hint that there's something wrong with that code. Okay, so Swift here is enforcing its law of exclusivity, which says that you can't reentrantly begin mutating the same thing twice. So here we started mutating V in test, where that ampersand is, right? And then inside of sort, instead of doing mutation through S, which was already under mutation, we went out and initiated a new mutation on V. Okay, and Swift is telling us that what we're doing here doesn't make any sense, and it doesn't know which of these mutations to keep. Okay. So, as I mentioned before, you know, I hope you won't walk out on me now, because most of these kinds of violations are caught at compile time. This one only happens dynamically because our example uses a mutable global, which, as Sean will tell you, is just as good as a shared pointer. Is that right? So you just can't do any better than a runtime check in this case. Okay, you allow mutable globals. The best thing you can do to protect people is a runtime check. Okay. So here are some examples of code that fails at compile time. Okay, so you're swapping X with X. Can't do that. Howard Hinnant will tell you that you never need to do that. And if you do, it's a bug in your algorithm. Okay, the second and third examples are essentially the same thing, first with a free function and then with a method, right? And so what we're doing is we're mutating a thing, and then I guess that should be X, right? We're mutating a thing and then also mutating a part of it through a separate in-out parameter. So those are overlapping references. And the one that might catch your attention is the last example, though. The compiler can't tell whether I and J are referring to the same position or not, right? So it has to reject that call. But if you look at the error message, you'll also see that the standard library develops something very much like C++ iter_swap to deal with this purpose, right? So a mutable collection has a swap_at method that takes two indices, and it can dynamically check for equality of the indices. And since in our case, we have to do the check anyway for safety reasons, that's a no-op if they're equal. Sorry, Howard. All right. So, as I already said, we casually use pass by mutable reference when we really mean in out, because it's inconceivable to us that we can actually be expected to reason about values without independence. According to the standard, all references mean something we don't normally intend. Okay, if you take the strict definition of the standard, they don't have to be independent. And when we take parameters by const reference, do we think about who might be mutating the storage behind our backs? Not you, Lisa. Everybody else. Do we think about that? No. No, that's a free transformation that we make from pass by value to pass by reference because it'll be more efficient. But what we really mean is it's pass by value. Just do it efficiently, right? And when we take a double ampersand reference, are we ever trying to signal to the caller that if they pass us an R value, that we might or might not consume it? Not really. What? Yeah, that's the whole point, that it doesn't matter to the caller.
No, the whole point that you're telling that it's a sync.
No. So yes, what you're saying is, but if it's a sync, that means you are going to consume it.
Right.
Not that you might or might not.
I'm going to consume it, but it's undefined what will be left. I may consume part of it, I may consume all of it, I may decide not to consume it at all.
Okay. Yes, you can do that. Does that happen in practice?
Yes.
In the back?
Say it means you have to conservatively assume it will be consumed.
Yeah.
Even if it's only 1 in 100 times.
Yeah, Daisy says means you have to assume that it will be consumed conservatively. That's right. It does.
Yeah, it happens in practice all the time. Condition, you pass arguments, there
Yes.
is a condition.
That's not the question. Are you trying to signal that to the caller?
Yes, absolutely.
You're trying to tell them that there might be a useful value left here.
No.
No, you're not.
No.
Right. You are consuming that value.
I'll tell you never use it again because you don't know.
Exactly. That means you're consuming it.
Well, yes.
That logically, this is about the contract between the caller and the callee, right? And what the signals are from your argument passing convention, what they mean to the caller, and what they mean to you as the callee. All right? And all I'm saying here is that when you pass by R value reference, it's never a signal to the caller that there's some condition under which some condition under which they might actually be able to use that object, right? You would have to give them a flag somehow, and we don't do that. It's just not, that's not a normal programming practice. Yes.
One example of where we do that is try and place.
Yes.
Which is
Oh, God.
the key is the first argument. Either move from the value constructing arguments or not, depending on whether the key already existed in the map.
Yes, but the question is, do you signal to the caller that you did or didn't move?
It returns the return value, an iterator and bool pair saying where is it and was it inserted.
Yeah, that's not what the purpose is, but okay, fine. You can read in the tea leaves, you could get that information by a side channel. Okay, fine. This is about intent, okay? What I'm trying to talk about is the intent that we signal when we program. Not what you can do, not what you can deduce from code, but what we mean when we write code. And I'm saying that we don't use the expressivity of C++ references the way habitually, at the degree to which the standard allows it, okay? And when we don't, right, the compiler though, the compiler is more like Inigo Montoya, right? It knows the meaning of these words that we're using, and it knows it needs to obey the rules, right? So not only does that mean it needs to let our clients do stuff that we're not really prepared to handle, like mutating a thing while we're looking at it through a const reference. It also can't make any assumptions about which things might be changed by an opaque function call, right? And so that means lost optimization opportunities. All right. So I believe, so are we at time? 0? We're at wrap-up time. Okay. Yeah.
If you want to take another 15, please go ahead because of the delays.
Okay. Does everybody want to go for another 15?
Yes.
All right. Let's do that. Okay. Okay, so now I'm going to shift gears a little bit and talk about the problem of value semantic arrays in Swift. Okay. So first, we need to understand some of the baseline design constraints of Swift to understand the problems I was facing with this. The first requirement was interoperability with Objective-C. Apple has an enormous investment in existing frameworks built with this, and nearly all of that stuff needed to come into Swift without, too much impedance mismatch. So Objective-C is basically just C plus a system of reference counted classes with dynamically dispatched methods. It's almost like Python classes, almost. Okay, so that's the first thing. Second, it was to be safe by default. And so what does that mean? That means two things. One, safe APIs can't cause undefined behavior. That's the definition of safe for us, although there's a caveat. So they will stop the program if that's the only alternative, right? If they have to stop the program rather than get into undefined behavior. And if you have to make an API that can't do that, that's an unsafe API. Nothing wrong with an unsafe API. Okay. The second thing is that the programmer needed to be alerted when they're using an unsafe API. And so rather than putting a feature in the language to do this, we actually just used a naming convention and it worked great. So we put unsafe in the names of things. So for example, C pointers are called unsafe pointer in Swift. This works really well and avoids the weight of a language feature, right? And experts can still build safe components from unsafe parts, which is great. But there is the caveat I was going to mention is that safe by default did not include thread safety and still doesn't in Swift. Okay, they chose a different mechanism for isolation than inherent thread safety. Okay, so you can still, for example, you can have a global variable and you can have a race condition on a global variable. All right. Finally, the last thing, all types are copyable and assignable in Swift. And that means no move only types, right? That's something that Swift wants to address down the road, but it was, not a priority for version 1. So it wasn't built in at the foundation. Also, not on the list of things that Swift had, copy constructors and assignment operators. So I'm thinking, okay, no copy constructors, no assignment operators. How am I going to build an array with value semantics? So I went to talk to Doug, my friend and the lead language designer, about copy constructors, and he said something really profound. He's like, I don't want to go down that road. No, sir. So, well, what am I going to do? I said, I'm going to be sick if Swift ships with reference semantic arrays. I mean, really, like that was my, aside from, it was reference semantic, value semantics and generic programming. That was my whole mission in Swift. He just sort of shrugged unsympathetically and said, use copy on write. And then he kicked me out of his office. So I had some reservations about this copy on write approach, because the first thing I remembered was that GCC's string implementation used to use copy on write, but it was taken out for C++11. And I didn't know the details, but it had a reputation for being disastrous for multi-threading. And this is one of those lessons that I internalized from my time with C++ and assumed that it would present the same problem for Swift. It turns out, though, that the real problem with C++ and copy on write comes from the fact that C++ containers are exposing unsafe pointers and references to their internals all over the place. So you can't even read an element without touching an unsafe reference, which could then be persisted and for which C++ makes stability guarantees. And so if you want to read all of the gory details, there's this wonderful gist of Alf P. Steinbach's where he explains it all. But anyway, since Swift collections were not going to expose unsafe references, right, safe by default, that wasn't going to be a problem for us. So this was an area where Swift's policy of safety by default actually opened up some new design avenues. So we ended up with a layout like this. Who thinks arrays should have 3 pointers? Yeah? Yeah? Okay. All right. So is John Lakos in the room? Yeah. Hi, John. I remember years back when I was challenging you about allocators and you said, because I was saying, you know, we can't make these containers any bigger when they're empty. You know, that's not okay. You said, how big does the vector have to be? And I was like, oh, just, one word. So I remembered that, okay? So size of array is 1 word. Yeah, that's really good if you have a lot of empty arrays, which happens. Okay, so let's look at how mutation works here. So if we have X here is an array that contains C and D. I don't know what C and D are, they're just some values, okay? And we say insert B at 0. Okay, the first thing that happens is we check the reference count, and if it's unique, we can do a mutation in place, right? This uniqueness check, by the way, is extremely relaxed. It's a very relaxed atomic because false negative for uniqueness, false negative for uniqueness is just some, you know, a little efficiency, and that's rare. So yeah, it won't affect correctness. Okay, so this is why you want reference counting and not a garbage collector if you care about value semantics. Because in-place mutation is important. Okay, so now if we copy this thing into Y, we have another reference, right? And now we have a non-unique reference count. But notice, this was an order 1 copy of an array. In fact, because of the constraints that I was working under, the only way to make a variable size data structure was to use reference counting.
How do you increase the reference without copy constructor?
Copy constructor of what?
Of your vector.
So the vector is this thing. Okay, this is in C++. There aren't any copy constructors.
Right.
Okay, and this isn't an assignment. This is an initialization, right? We have the same problem as C++ does in this regard, right? So what I'm doing is constructing a new vector, and because I don't get copy constructors, I can't override that behavior. That's all built into the language. So copying anything in Swift is there's a bag of trivially copyable bits and some counted references. That's the model.
Got it. Okay, so references are just like part of Swift language.
They're part of the language because we had to have these reference counted classes as.
So the idea is if you have a reference to anything, then that thing has a reference count. When you copy the reference, you increase the reference count.
Yes. Yes, that's right. If you have a reference to anything, then that thing has a reference count. Yeah, no, there are raw pointers too, unsafe pointers, but these are not unsafe as long as you don't try to share them across threads, because I said thread safety was off the table. That's Hand wave. Okay. Right? Okay. So now we have to do something different because we had a non-unique reference count. So we allocate new memory, and what we do is we build the new value in place. Right? Notice that there were no copies here. We had a mutate in place and to build a new value. Right? So copy on write is kind of a misnomer. Right? It's not that. Sorry?
What do you mean no copies? Like the new
I never made a duplicate of this and then moved all the elements down.
But you copied all the elements. You
I
made a copy of B.
There were copies of the contents, yes, but it isn't what typically people think of. Okay, I'm going to make something copy on write. I'll just use the copy constructor before any mutation, right? And that's extremely inefficient because what you do is you end up copying this, and then you have to go over all of the memory again to move it.
So it's built into the insert function.
It's built into the insert function, yes, into all of the mutating functions on array, yes.
So the B and Y could be the same B as an X with reference counter 2, right? Because these things are regular reference counter way down.
No, there are structs. There are trivially copyable bits. So an int is not a reference.
But it could. Is that the case?
No. In Swift? No.
So you not have an array.
Oh,
Yes.
yes. In this array, these things could have been references to classes. That's true. But so just for the record, the only thing I use classes and references for in Swift is to implement value semantic copy on write. Okay, I never touch classes. So if you want, but they're in the model for the language, and if you want to use them, yes, you might end up with two things that are referring to the same memory over here. Okay,
Does this have to be
5
completely
minutes.
copyable, or can it throw
Does what have to be?
the data, the B, C, D?
Yeah, there are no copy constructors, and the compiler copies everything in one way. So it's copy the trivially copyable bits and increment some references.
So
That's it.
So it never throws.
It never throws. So and this is a really I'm glad you asked about that, because it's one of those things that I forgot that really impressed me. Like, it changes the way you think about programming when copy can't throw, right? In fact, the whole model for error handling in Swift is very different in the sense that Swift doesn't consider out of memory a recoverable condition. It says, okay, on the platforms this is running on, there's virtual memory, and if you run out of memory, it's too late. Your process is going to get killed anyway, so we don't care. And that changes the whole calculus of how you do error handling, because very, very many fewer things can actually fail. Marshall.
No, my hand swells if I keep it down.
Okay. Sorry. Feel free to raise your hand. Yeah. So, okay. So I got about 5 minutes left, and I'm gonna go through the next bit, and then we should wrap up and have questions, which is what we're doing. Okay. So this system of having these built-in references in the model, built-in reference counted references, opens up some interesting possibilities. So, for example, Swift is in Godbolt, so you can look at this yourself. But here we have a function foo that takes an array of int and returns the first int, but first it copies the array into y, right? Now, because reference counting is a fundamental part of the object model, the compiler can see that the reference count traffic accounted for by copying into y is redundant, and it can eliminate it. And if you compare that with the C++ version using a shared pointer, You see I had to make the font really small so I could fit all of the C++ code that's generated there. And this is not because Swift is better than C++. This is because C++ doesn't know about the semantics of its reference counting, right? This is built in a library that has no special meaning to the compiler. Whereas Swift does know. Swift knows where an increment and a decrement are a pair, and that if you do another increment in between those, it doesn't care. It doesn't need to do them. All right. Next, the compiler can tell that once I've appended 3 to X, now I know that that array has a unique reference to its buffer, right? So there's only one uniqueness check in the code for this function. You're looking at that one, all right? So in theory, you can hoist a uniqueness check up through complicated algorithms that are doing many mutations. And
The mechanism for the elision of that check.
there was a performance group that knew how to write optimizers, and I said, I want this thing to be elided, and they said impossible, and I said no, I really, really want it to be elided, and they said okay, we'll do what we can, and they worked a miracle. This is what I know. All right. Oh, it's in our paper. Okay, yeah. Dimitri says it's in our paper, so read our paper. It's actually a very readable paper, in my humble opinion. If like the theory part is theory and it's dense, but there's a lot of exposition that's actually like sort of readable by humans. Fine. Okay. So now I think we're at the limit. There's a really cool thing I want to tell you about. So maybe we will have an evening session or something to pick this up, because my voice is going to wear out, and I'd like to talk to you all more about this. Thank you all for your time here. It's really great.